Good afternoon, everyone. This is Rebecca Power, and I would like to welcome you to The Current, the North Central Region Water Network's Speed Networking webinar series. The purpose of The Current is to increase your access to university extension programming and research that we hope will be useful to you in your own work. The format is three 10-minute presentations with questions and discussion at the end. So we're going to hear all of our presenters today and then encourage you to submit questions via the chat box, which I'll say a little bit more about in a minute. All the webinars that we've done have been archived on the North Central Region Water Network website at northcentralwater.org. So those are available for you to review at your leisure. Our topic today is managing agricultural drainage, and thanks to Chris Hay from South Dakota State University for organizing this session and for being one of our speakers. You'll also hear from Jane Frankenberger from Purdue University and Richard Cook from the University of Illinois. And I will tell you more about them right before they speak. This webinar is the 8th in our series, and I'll just give a quick commercial for the 9th. That webinar will take place on June 17th at 2 p.m. Central, 3 p.m. Eastern, same time. And the topic of that webinar will be cover crops, and we're being assisted by the Midwest Cover Crop Council and Dr. Dean Boss from Michigan State University in putting together that session. Just a few tips for a smooth experience. I'm going to back up here for a minute. For those of you that are speaking, we have those folks on a headset with a microphone, and if you end up speaking to ask a question, using that headset and microphone for best results is often the best. Please submit your questions to presenters via the chat box, as I said earlier, and that's typically in the lower left-hand corner of your screen. We'll be monitoring those and collecting them and synthesizing those for the speakers at the end of the session. If again we have the opportunity for interaction, depending upon the number of participants that we have today, please raise your hand. There's a hand icon, again, somewhere probably in the left-hand part of your screen. So raise your hand and one of the moderators will call on you, and then you'll need to press the talk button, which should be further up on the left-hand part of your screen with a little microphone icon, and we will call on you. Okay. As I said, these are today's speakers: Jane Frankenberger from Purdue University, Chris Hay from South Dakota State University, and Richard Cook from the University of Illinois. So let's get into our introductions. Jane Frankenberger is a professor of agriculture and biological engineering at Purdue, where she focuses on water management and water quality in drained agricultural watersheds. She works with the drainage industry to improve water management practices and with conservation agency staff and citizens to manage watersheds more effectively through the Indiana Watershed Leadership Academy and other water quality programs that she leads. Over her 19 years at Purdue, she has benefited greatly from interactions with other water specialists across the North Central region and is looking forward to working with many people across the region in the new project she will be describing today. So what Jane has done here briefly, one of the purposes of these webinars is to help extension educators, other university folks, and our partners, whether they be from local conservation departments or federal agencies, state agencies, farmers, environmental organizations, people that are interested in water resource management, in learning more about the resources that they have access to across the North Central region. And Jane is one of those resources. So Jane, take it away.
Okay, well, hello everyone, and I'm pleased to present an overview of a new project that we have, and I'm presenting this on behalf of quite a large team, the core members of which are listed here at the bottom. I won't take time to read them all now, but you can see that we represent most of the North Central region, plus North Carolina. I also want to acknowledge funding from USDA NIFA through the Water for Agricultural program. The official title for the project is shown at the top, Managing Water for Increased Resiliency of Drained Agricultural Landscapes. But as we've talked through our ambitious goals for the project, we determined that a short statement of what we hope to accomplish is transforming drainage. So it's a huge goal, and we won't get there in 5 years, but we will lay a foundation, which I'll talk about today. So tile drainage, as most of you will know, is a very widely used practice on poorly drained soils. And it's used to increase crop yield in all locations, and in some locations actually is needed to make agricultural possible. But the widespread use of drainage also leads to a widespread concern, which is the increased nutrient losses to rivers and streams that tile drainage causes. This is especially true for nitrate, which we have been trying to address for decades. And more recently, the scale of phosphorus loading into tile drains has also become more widely understood. So now we really are talking about nutrients, both nitrate and phosphorus. So these nutrient issues are important at the national scale, both hypoxia in the Gulf of Mexico, which is primarily a nitrate concern, although also phosphorus, and toxic algae in various lakes, but most recently in 2015, the terrible situation in Lake Erie in Toledo, where 500,000 people were without drinking water for a few days, I think shook a lot of people up and really got back to the need to really become serious about addressing phosphorus. And some portion, nobody knows for sure, but maybe something like 50% goes through the tile drains. Our project also addresses a second issue, which is not directly related to nutrients, which is that even in the relatively humid Midwest, crops often suffer from a lack of water. And this was driven home in the drought of 2012, but water deficits occur nearly every year. And in response, irrigation has become more widespread throughout the region, even in places where irrigation has not typically been used. Both of these issues, so the excess nutrients that I talked about at the beginning and then the lack of water in summer, are expected to become worse through climate change. As we expect warmer and wetter springs, that will exacerbate the nutrient issues, and drier summers are also expected, which will exacerbate the crop water deficit. So what we've been thinking about, and this group of researchers and extension folks from across the region, is the need to retain drained water in the landscape to address both of these issues. So the question is, where can you retain water in a typical field that looks like this? So we've thought of a few places. One practice is called drainage water management, and in this practice we actually retain the water in the soil of the field. And I'm not going to go into it in detail because I believe Chris Hay will be talking more about some of the research that's gone on. So that's one possibility, retaining water in the soil. Another is to retain water in the buffers, and there's a practice called saturated buffers, which has been it's being researched across the region. So it retains water in the buffers. And then the third practice, which is much less common and hasn't been studied as much, is what we're calling drainage water recycling. It also has a few other names. But the idea here is we have a pond or a reservoir, and the subsurface drainage and also the surface runoff are actually captured in the reservoir and then pumped back onto the cropland to be used by the crop later in the season. This is a great practice. It's not new. There's been research since the 1980s that have addressed that. The image there is of the wetland reservoir sub-irrigation systems that were put in Ohio in the 2000s, and there's been several papers that have published the crop benefits of those. There's also been systems in Ontario, Iowa, Missouri, Illinois, and folks in Canada are trying to do this. But those would be just one system. It really is not widespread at all. But if these practices, so we've got 3 practices, if they're not new, one would likely say, well, what is new about this project? And although these practices have been evaluated in various locations across the region, what we're going to do in this large new project is to try and bring the results together for improved decision making. And the map here shows the research areas, the places where there are data, many of which have already been published, but we're going to put them in one large database, and so that much more synthesis and recommendations can come out of them. So that's the big new effort that we'll be starting all across the region. It's a daunting task, but one of the reasons we think we can do it is there's been another coordinated agricultural project that's been going on for a little more than 4 years now, called the Corn Systems Coordinated Agricultural Project, or Sustainable Corn. And so some of the data sets are already in the database, and it's taught us a lot about how to get large data sets together. So we're excited about doing more with this. This is sort of a diagram of what we hope to do in this project. I'm not sure I have a pointer here, so I'll just start on the left with Objective 2, which you see on the bottom. So we've got these 30 field research sites. Out of those, we're going to do Objective 2. Oh, let's see if I can do this. No. Objective 2 is synthesis, so we'll be working on that through the database. Objective 3 has a lot of modeling to extend the findings, and both of these will also look at the economics, because I didn't mention that yet, but obviously the economic barriers are the major barriers to getting these in place. So we'll be seeing how we can address those. Then out of that, Objective 4 will be tools for decision making, and then Objective 5 and 6 are extension and then education to graduate students and teachers. But what I want to end with is the Objective 1 that's across the top in this image, which is that one thing that's critical to make this project successful is the network, which we already have within the project team itself. I showed the team on slide 1, but we have many collaborators that I didn't necessarily list here and stakeholders, and we're looking to expand that even further. So the expanding and strengthening of the network that can include all these sorts of people here is a goal of the project. So from the top, we've got farmers involved, the drainage industry, researchers, the Natural Resources Conservation Service, which makes decisions about conservation practice incentives and cost sharing, and technical standards are critical. We have drainage contractors involved, the U.S. Fish and Wildlife Service, because especially as these ponds would have aquatic ecology effects, nonprofit organizations like the Nature Conservancy, and state agencies. So these are all critical. And one of the ways they're involved are through an advisory committee. So I thought I would just put this up because I had this slide that shows some of the broad expertise that we have on the advisory committee for this project. But more important is you who are on the call might be able to be part of this as well. So I thought that I would just say contact me with an email address. As of today, we don't yet have a website. This is a very new project. We just had our kickoff meeting a few weeks ago, but we will have a website and many ways that we hope people will get involved. So that's the goal, nothing short of actually transforming the way that we do drainage. What our sort of our short-term outcome is that by the end of the project, producers will be able to access the research-based information that they need so that they can make informed decisions about retaining drainage water in the landscape. And that should lead to increased resiliency. A longer-term vision, probably beyond the scope of this project, is that the process of designing and implementing agricultural drainage will actually be transformed so that water retention in the landscape is at least considered every time a new drainage system is put in. And so once again, the nitrate and phosphorus losses that are having such a negative effect on our streams and rivers the nitrate and phosphorus can go back onto the tile drain, and back onto the crop field, and actually although it still might come out through the tile, it can be eliminated from our rivers and streams. So Chris Hay is going to talk about one of those practices, and Richard Cook will talk about another related practice, so that will give you more information. Thanks so much.
Great, thank you, Jane. And please remember questions for Jane or questions that are coming up about agricultural drainage more broadly, please put those in the chat box, and we will get to them after our third speaker. Chris Hay is next. Dr. Chris Hay is an assistant professor and extension water management engineer in the Department of Agriculture and Biosystems Engineering at South Dakota State University. His research, teaching, and extension programs are focused in the areas of agricultural hydrology and water management. Examples of his research include studying the impacts of subsurface drainage on hydrology and water quality in transition from subhumid to semi-arid climates, and impacts of drainage and cover crops on evapotranspiration. His extension programs focus primarily on drainage, irrigation, and water quality, and he has been recently leading a program to train NRCS staff in the North Central region on drainage water management. Thanks, Chris. Chris, maybe press your talk button. Hopefully we can hear you then.
Yep, that would help. Good afternoon, and thanks. And as was mentioned, I'm going to be talking about a specific practice here called managed or controlled drainage, which is one of the practices involved in that new project that Jane mentioned. Again, this is not a new practice, but one that's been around for a little while. And so, although there's certainly still some research questions associated with it, there's also a lot that we do know about the practice. And what we're talking about with this practice then is using control structures to actually manage the timing and amount of drainage that we let leave that drainage system. As it was being developed in North Carolina, oftentimes that was done by actually managing the water level in the outlet ditch. But as it's transitioned here into the Midwest now, most often that's a control structure actually placed in line with the drain pipes themselves. And a little bit of semantics here. When the practice was being developed in North Carolina, that practice was typically called, and still is called, controlled drainage. As it shifted and started being applied here in the Midwest, there's some concerns about the term control of drainage, and so drainage water management was really coined as the term for that practice. But also there's been a kind of a shift where drainage water management has also started to take on some other practices related to this specific practice, and so sometimes that's a little bit of a source of confusion, but when I talk about controlled or drainage water management here, I'm talking about this specific practice. And one of the things that was coined by Wayne Skaggs, who's one of the preeminent drainage researchers here in the U.S., was this idea of the golden rule of drainage, that basically we should drain only what's necessary to ensure trafficability and good crop production and not a drop more. And so drainage water management is one of those practices that fits right in with this golden rule of drainage by actually managing that drainage instead of just allowing drainage to occur anytime the water table rises. And key concept behind that is when we look at patterns of precipitation and evapotranspiration, so the precipitation, the line in blue here, and evapotranspiration, the line in green here, rarely do those precipitation, the amount of water we receive as precipitation, the amount of water demand we have for evapotranspiration, rarely do those line up the way we would like them to. And so there's periods of the year where there's potential for excess water and potential for need for drainage, and then there's periods of the year where likely there's some water deficit. And certainly the soil can help buffer that, but there's going to be times of those excesses and deficits of water. And so the level of drainage that we need varies over the year, as well as the level of the demand for water varies over the year. And so again, drainage water management allows us to manage that drainage to better address both that excess and deficit water condition. But another important concept is that drainage water management only manages the drainage outlet, or the amount of drainage that we're letting leave the field. And so we've got water entering the system as precipitation, a large amount of that water leaving as evapotranspiration, some going to deep seepage and some running off the field, as well as the water that's leaving via the drain flow, but only drainage drainage is the component that's addressed via drainage water management. So although you may hear about controlling the water table with drainage water management, that's only true if we've got enough water in the system to have that water table to control. And so if the precipitation isn't enough to actually raise the water table, then drainage water management won't have any impact. If we want to actually raise the water table in that situation, then we've got to supply water through sub-irrigation to make that happen. Another concept is that it's really limited to situations of flat topography. And so if we get more slope, we lose that ability to manage, and so we can deal with that somewhat by introducing more control structures, but at some point that gets impractical. So we talk about a 1% slope or less is where this is really applicable. But that's still a large area of the north central region that still lends itself to this practice, about 31 million acres by this estimate that would be suitable. When we look at some of the results of the research on this practice, this comes from an article summarizing a 5-state CIG project in the Midwest on this practice, as well as the results from other areas where this has been researched. And overall what we see is a reduction in the drain flow, so the amount of water leaving the field via drainage, that reduction ranging from 18 to 85%. Then when we look at the impact on nitrate losses, then another thing that's been pretty consistent from the research is that drainage water management has little or no impact on the actual concentration of nitrate leaving with the drainage water. And so really the reduction in nitrate loading leaving the field is primarily from that reduction in the drain flow. And so the reduction in nitrate load pretty well matches that reduction in drain flow. And so 18 to 79% being kind of the range of nitrate load reductions that we've seen from the multiple sites that have looked at this practice. And then again, this is a practice that hopefully benefits the environment, but also potentially has some benefits to yield or to production. And so again, kind of summarizing the research that's been done on this practice, when we look at the impact on yield, there's been several cases of yield benefits or yield increases because of the practice, because of the ability to conserve some water at times. And so that's ranged from 1 to 19%. Although up to 19%, those yield increases tend to be fairly modest, more like 1 to 5%, up to 10% in some cases. But in many cases, there's no real effect on yield, and a lot of that just depends on the timing of rainfall. And so if we don't get timely rainfall at times where we can capture it, then there's really not going to be much of an impact on yield. Typically haven't seen reductions in yield, although there was one case in some of the research that did show a yield reduction on one site. But there is that potential, if the system isn't managed well, that we can have some reductions in yield if we don't manage that system well at times when there is some excess water after the crop is in the ground. If we look at how the practice is typically managed, and certainly there's different scenarios that can be used. This is just one typical scenario. Once the crop is harvested in the fall, we would put some of these weir boards or risers or flash boards in the control structure to raise that drainage outlet. And so then the water table would have to rise all the way to that level to be able to actually flow out of the system as drain flow. And so once harvest is done, then at that point drainage really isn't needed in the field, and so we can put those risers into the control structure and then hold back any water into the field that does occur over that non-growing season when the drainage isn't needed. And so by holding back that water, we hold back the nitrate that would leave with that water, and so again we reduce the amount of drain flow, and then we reduce the amount of nitrate leaving with that drain flow. And so typically those boards would be placed within 6 inches of the soil surface, or maybe about a foot below the soil surface, but raising up near that soil surface to hold as much water possible back over that non-growing season. And then in the spring, when the drainage is needed so that the producer can get out in the field for spring operations and planting, then we would pull those boards, turn it back into basically conventional drainage mode, where we would lower that water table all the way down to the tile elevation, let that system drain out, and let the field dry out so that we can get in a timely fashion and do those spring operations. And then allowing a little bit of time for some root development and to get the crop started. then we could put another set of boards back into that system to raise that outlet elevation. In this case, a typical level may be 2.5 feet below the soil surface, and now building in that capability that if we do get some timely rainfall, to capture and store some of that water in the field and make it available for that crop later on in the growing season. Again, that's just one scenario. There's other scenarios depending on the goals of the producer as well as climate and other issues. But if we look at that throughout the year, then again, kind of starting at the beginning of the year, coming off of the last growing season, we've got those boards in the field to hold back that water, reducing drain flow and reducing nitrate loss with that. Then in the spring, when the drainage is needed, we lower that outlet, let the system drain out, get in and do our spring planting and other field operations, put the boards back in, and then with the idea then of potentially conserving some water, which also will reduce nitrate losses, but also save some water for the crop to use. Then when fall comes around, if we need some drainage prior to harvest, we can pull some boards and allow that to happen. If we don't need the drainage, then we can just leave the boards in. And then again, once harvest is over, put the boards back in to hold that water and potential nitrate loss back. But again, that's just dependent on the outlet elevation. The actual water level is going to still depend on precipitation and water losses from evapotranspiration and other losses. And so while we might like to have the water table where those blue lines are shown, this might be one typical scenario with the orange line here where, again, we've got some excess water in the spring, we drain that out, and then maybe get a shot of rain in the spring where we can save some water. In this case, we actually show it coming up a little bit over that, and so we would still have some drainage to get it back down to the elevation we set. But then as we move into the meat of the summer, then evapotranspiration exceeding precipitation enough that the water table drops and we're no longer controlling that water table. And then showing again some water starting to build up in excess in the fall after the crop is harvested. This has become a priority practice from NRCS because of its potential for both reducing nitrate losses as well as improving production. And it's a focus of the Ag Water Management team within NRCS, and I see some of them have joined us. And so one of the things that we've partnered with NRCS on is actually doing some training for those employees. So it's been a hybrid approach, and so there's a number of online modules that have been developed to address this practice and some related practices. So there's 8 of those modules that are out there. Those are available for folks that would like to view them and like to learn more about this practice as well as, again, some of the related practices. They're available at this forestrywebinars.net site. Probably easiest to just go to that site and search for drainage water management, and you'll find those online modules. Also did a series of on-site training sessions with those employees across the 10-state region and the North Central region, training just under 600 employees in that region. Another thing that we'll be doing as part of that project is actually our own little upcoming webinar series, hopefully starting this next month. Here's some of the topics that we'll be covering that, and so we'll certainly be getting the word out through the North Central Region Water Network as well as other outlets. And so again, if it's something you're interested in, keep your eye out for those webinars. And with that, I'll close off and turn it over to Richard.
Great, Chris, thank you. And why don't we just move right on to Richard here. So Richard Cook is professor and drainage extension specialist. You're probably seeing some commonalities here in the Department of Agricultural and Biological Engineering at the University of Illinois, and an adjunct professor in the Department of Agricultural Engineering at Nala University in Sierra Leone. He holds a bachelor's degree in agricultural engineering from the University of West Indies, Trinidad, a master's degree in agricultural engineering from the University of Guelph, Ontario, and a PhD in agricultural engineering from Virginia Tech. His current research focus is on the development and evaluation of drainage-related best management practices for improving water quality, watershed-scale monitoring of subsurface drainage systems, the development of multi-objective design criteria for subsurface drainage systems, and the design of rainfall harvesting systems. He also developed the online version of the Illinois Drainage Guide. So Richard, I think, is a master of all trades, and we're happy to have him here with us today. Go ahead, Richard.
Thank you very much. It's indeed a privilege for me to be a part of this webinar. I won't spend too much time talking about the effects of nutrient on, say, the hypoxic zone, because this is well known to this audience. I'll suffice to say that we are developing subsurface bioreactors for use in the Midwestern region, which is heavily tiled, for dealing with some of these nutrient loss problems. Now, bioreactor is essentially a trench filled with wood chips through which tile water is diverted, and then water is treated before being passed back into the system. It consists of a diversion structure as well as a capacity control structure. This is like a top view of the bioreactor. Water flows through the medium. The two ends aren't connected hydraulically. It's just flowing through the medium. And a side view, the flow is controlled by the level of the stop logs or the weir boards in the diversion structure and the capacity control structure. The distribution is not necessarily linear, but this is probably the best approximation that we can show of the process. We also have structures where the two control systems are combined. The two structures are combined, and in these systems there's a chamber which causes a diversion into the bioreactor, and another chamber through which we can control the capacity. And these are easier to install, although they can't be used if the structures are too big. The area treated is too large. In designing these bioreactors, there are several factors which we should consider, which leads to uncertainty in the performance of these systems. One is the use of a soil cover. In certain areas, a soil cover is put on top of the bioreactor, and this soil cover, it reduces the hydraulic conductivity of the flow through the system, and so the flow will be less than the design flow. So if it's necessary, then one can be put on, but otherwise there is no need to have a soil cover if, say, there's a bioreactor at the edge of the field in a filter strip. It has a very small footprint, these systems do. Then another factor is the conductivity. In designing systems, we usually use a conductivity value from the literature. And if we can determine a conductivity from a particular batch of wood chips, then we will have less uncertainty in the use of the system. We also use a constant conductivity. However, what our research has shown that the effective conductivity in the bioreactor is not a constant. The conductivity decreases over time, and then when there is a spike in flow, then the conductivity increases again, and then it falls back down. We think it's due to the formation of biofilms in the inside of the bioreactor, biofilms on the medium. Indeed, we have found, looking at the cross-correlation coefficient, that there is a strong correlation between the conductivity and the flow 6 days prior to that event. So it's possible then to develop some kind of model, say a Markov chain model, and to treat the conductivity not as a constant but as a variable. And this will reduce our uncertainty in the results. And there is the residence time. The residence time is controlled by the level of the upstream and the downstream stop logs. And we can increase the residence time by decreasing the difference between these two heights. But if we decrease the residence time, if we increase the residence time, we are decreasing the flow through the system, and then there's a greater potential for bypass flow bypass in the bioreactor. So we need to determine what is the optimum board settings to get the optimum performance of the bioreactor. And in our model which we have developed, there is room for playing with the settings to determine what the optimum settings would be in the system. If we want bioreactors to be used more widespread and to be used in things like water quality trading, then there is a need to reduce or to identify any type of adverse effect and to deal with them. We have looked at some unintended consequences of bioreactors. For example, we find that almost invariably there's a slight increase in the dissolved reactive phosphorus coming out of the bioreactors. This is especially true when the bioreactors are new for the first few months. And although the values are small, in this case they are less than 0.4 milligrams per liter, yet it's real, and it happens almost every time, as you can see from most of the literature. And people are working on ways to reduce this phosphorus, either by adding medium to the wood chips for phosphorus removal or adding a separate chamber for phosphorus removal in some of these systems. Then we also looked at dissolved organic carbon, which increases particularly in new bioreactors and then settles down, but it's usually more than the inlet dissolved organic carbon. And of course, the dissolved oxygen is usually down to close to zero. The combination of high DOC and low dissolved oxygen can have some adverse effect inside of the receiving stream. And so we have to be able to model this effect. It's particularly important if we are thinking of scaling up this system so that we have a whole host of bioreactors out in the landscape. And methyl mercury. With our redesign of the system, we have addressed the methyl mercury problem, and indeed in most of the instances where we measure now, the methyl mercury coming out of the system is less than the methyl mercury entering the system. So we think that problem has been licked. And in any case, the levels are rather low. Here there are less than 1 nanogram per liter. The background level in natural systems tend to be of the order of 0.4 to 2 nanograms per liter. So it seems then that it's not a major problem. Now, we also have to make sure that our results can be replicated and we can predict how the systems can perform if we are moving from, say, one part of the region to another, or another part of the country. And when we looked at the bioreactor performance, we measure performance either or in terms of percent nitrate load reduction or nitrate removal rate. It seems that nitrate removal rate is a tighter measure of performance, in that the variance or the stochastic component of the relationship between, say, temperature and retention time and removal rate is less than if we look at the load reduction. The models which we have used and that I have developed, we have looked at the percent load reduction, and we're going to redo these models to instead look at the nitrate removal rate, especially if we can incorporate the effect of temperature on removal rate. And if we know the water temperature, we can do this. We can, the soil physicists say, we can predict the soil temperature at any depth in any location with reasonable accuracy. However, the water temperature of the water coming out of the tile at a given depth is not the same as the soil temperature. And so to reduce the uncertainty, we have to develop models so that we can predict what that water temperature would be. We have done some work on using solar energy, both active and passive solar energy, to increase the temperature in bioreactors, and we have achieved some modest success. We have increased it by between 0.6 and 2 degrees Fahrenheit, but there's much work left to be done, and this is one thing that we are going to be looking at over the next year or so. And if I could make some recommendations based on what we have learned about how we can reduce uncertainty in bioreactors. One is to incorporate a variable hydraulic conductivity, because that's what occurs in the system. And it's not hard to do. It's a simple Markov chain model will be able to achieve that. And if we can use removal rate instead of the load reduction to characterize the bioreactor performance, then we can produce results which would be more transferable and more predictable. And lastly, if we incorporate the effects of temperature, then again, we would reduce the uncertainty in our bioreactor systems. Thank you very much, and I look forward to any questions you might have.
Excellent. Thank you, Richard, so much. And now I'm going to encourage everyone again. I've been sticking a couple questions in the chat box here, but please, those of you that are participating from other parts of the region, feel free to put those questions in the chat box. And I will go ahead and start with Chris. Chris, I was just curious if you could tell us a little bit about what farmers are saying about why they're interested in or why they may not be interested in having drainage water management installed or being practiced on their farms.
Sure. I think, well, one, the farmers that are interested, part of that is they like that idea of a win-win solution where, they feel like they're having a positive impact on water quality, but they're also getting something out of that through some potential yield increases. One thing that we try to be cautious about is not overselling what that yield increase is, again, because it doesn't happen every year, and in the years that it does occur, it's fairly modest, but has been there. But we just don't want to get them overexcited about that. But I think a lot of it really comes down to the ones that are interested really like that idea of being able to manage their drainage. That we talk about, you wouldn't sell an irrigation system if you couldn't control how much water went through that irrigation system, but we install drainage systems where there's no control over that drainage. And so this, again, gives them that management tool that they didn't have before. The ones that aren't interested, then oftentimes that's because they're not interested in actually managing that drainage system. They like the idea that, well, the drainage system's there now and I can forget about it and not have to actually manage it. So that's probably the common themes I hear.
Great, thank you. And Richard, how many bioreactors have been installed across the North Central region? I wasn't sure if Jane's graphic was all-inclusive, or what can you tell us about that?
I think maybe Ruth Book can answer how much has been installed in Illinois. In Illinois, they started cost sharing on the system. I think it was last fall. Before that, most of the systems that were installed in the state were for purposes of research. And we installed, I would probably say, between 15 and 20 bioreactors over time in Illinois for research purposes. There have been other systems in Iowa and also in Minnesota. And these are the ones that I know about. There's at least one in Michigan as well, and maybe in Indiana, but I'm not too sure. It's a fairly new practice.
Okay, great. And Jane or Chris, did you have anything to add to that?
I guess I can add that we've got 3 that we've been looking at in South Dakota with potentially plans for a couple more. And so we're just getting started here in South Dakota. Certainly we're not as far along as they are in Iowa and Illinois.
And it's not widely used in Indiana either. There have been a few, but Illinois is certainly the leader here, and maybe Iowa.
Okay, thank you. And Sean has a question. Will it be difficult to characterize performance of bioreactors on removal rate, in parentheses, nitrate removed per cubic meter per day, if the flow is not constant? Won't the rate be 0 for any day that has 0 flow?
Yes, the rate will be 0 for days that have 0 flow. Well, what we have done in our model is that we have used like historic rainfall records through the DrainMod program, and then we can get like 30 years of daily flow, which have been predicted with the DrainMod program. And then we run this through the bioreactor based on the daily flow and the stop log settings. And hopefully we can incorporate the temperature as well. And then we'll be able to get a better idea of what the removal rate would be. Right now we are just using an average removal rate, but we can refine that, reducing the uncertainty in the measurement.
Okay, thank you. And Tim has a question. How much storage per acre is needed to significantly reduce nutrient losses?
And this is a great question, and one I don't have an answer for at this point, but is exactly what our new project will be addressing to get some orders of magnitude there. I'd also say there's many ways to consider what's a significant reduction of nutrient load losses. You know, sometimes we think it needs to be like statistically significant, but I think that's not really the question here. It's how many and how much is needed to bring these down, because all the practices that we're looking at have a very small contribution at the watershed scale, but what that means is we need a lot of them. But so you know, we can sort of avoid the answer that way. But I think your question is exactly what we need to start thinking about numbers, both how much nutrient losses we can get down and how much the ratio of pond volume to drainage area is needed, and then again to the area that water would be put on, for example. All these things we don't yet have numbers, but I think they're extremely important questions, so I'm glad you asked.
Okay, thank you. And Jen Flipiak has a question. What is the status of drainage water management and bioreactors regarding practice standards for NRCS cost share? That is, could a farmer get cost share through EQIP for each practice? Who wants to take that one?
But I can address certainly drainage water management, that there is a national standard for drainage water management, a practice standard for that, the 554 standard. And so yes, it is eligible for EQIP cost share. Again, it is one that has been a priority at the NRCS Ag Water Management team, and so there has been a considerable effort on trying to get increased adoption of that practice and cost sharing for that. And bioreactors, either Richard or maybe some of the NRCS folks that have joined us can fill in a little more on that. That one, I believe, is still a little more variable from state to state, that I think some states don't yet have a bioreactor standard in place and others do, and so that may be a little more state dependent.
Right, that's a good answer, and I would just say if anyone from NRCS wants to type a response in the chat box, that would be great, but that I believe that it is variable state to state still for bioreactors.
I know that in Illinois, the NRCS has started to cost share on bioreactors, and they have been cost sharing on drainage water management for a while, so they're both available for EQIP, and Ruth, I see she can probably provide more information on that.
Okay, and I would just add that NRCS is very actively looking at all these practices. There is a team that gets together and makes sure that the latest research is used and put into the practice standard. So it's a very active area for NRCS, as Chris said at the beginning. It's a high priority.
Excellent, thank you. It looks like Ruth has some more, another response here. The denitrifying bioreactor is an interim practice. Illinois and other states have adopted it and are providing financial assistance. And just for all of you, I'm reading these just to make sure that when other people are viewing the webinar after we're done, that they hear what some folks have said in the chat box. Well, Jane, I have a question for you. I know you're just starting on your big new project and working with others on that project, and that you need some time to get some work done. But I know we're going to be seeing some results from you before the 5 years are over. And can you tell us, when we might expect to see some things, some results of various kinds coming out of the project?
Oh, well, there's a good question. So some of we're using existing field sites among others. So some of the sites have several years of data already, and so we hope more synthesis could be done in the first couple of years. Also, the economic analysis should be done in the first couple of years. And the kind of questions like were asked about what would be the benefits that we could expect from various sizes, those kind of things we would have in a couple of years. Then starting them, we'll start to build tools that others can use, so that's sort of in the 2017, 2018, and then we'll be doing a lot more extension in 2019. So for sure, we'll be back to give talks in 2019 if you can schedule us, Rebecca.
Okay. Thanks for the warning. I guess I'll ask one more question related to drainage contractors, and I think all of you, have been doing work with the drainage contractors in your states and perhaps across the region, and I'm just wondering how those folks are responding to these various practices and in implementing them.
In Illinois, the contractors have taken to these practices like fish to water, and indeed the LICA, the Land Improvement Contractors of America, the group that I work with in Illinois, they have introduced a certification category for the installation of drainage water management, and so they have training sessions on this practice, and they are thinking of doing one also on bioreactors.
And I can say the same in Indiana. There has been a great deal of interest by the most forward-looking contractors in becoming certified as technical service providers for this. And one of them, who was the president of the National Land Improvement Contractors, I asked to be on an advisory committee for our project and was really impressed by how quickly he said yes and enthusiastically. So that we'll keep up that dialogue in all kinds of ways. So it's a good question. It's a very important audience that we work with.
And I guess speaking for South Dakota, we're a little bit of the Wild West here in drainage. That a lot of new drainage that's gone on here in areas where there wasn't drainage before, and so until recently, our contractors have just been so overloaded with waiting lists that there's been some hesitance to try and spend some time on actually designing systems for drainage water management or some of these other practices. So there's been some interest from certainly the more progressive contractors, but a lot of them have just had their plates full and haven't taken the time to really look at these more specific practices. But now that things have slowed down a little bit, I think we're seeing more of an interest, and some of that's being driven by the producers that are forcing the contractors to look at some of these systems because of the producer interest in actually having some of these systems.
Great, thank you. And for the purpose of our post-webinar viewing audience, Tim asks, what is the status of the practice standard for saturated buffers? And Ruth answers, it's an interim practice standard, i.e. experimental, and fewer states have adopted it so far, fewer than the other practices that we've been talking about today. And then she also says, some states like Illinois are waiting for results from research through Conservation Innovation Grant, so we know more about how to design them. Any comments from our speakers on saturated buffers?
No, so I know that there are about 15 that have been installed through these Conservation Innovation Grants, and the research is just starting to come in, so that is the newest practice, but I think it seems promising. I think the issue in our especially in many of the flattest lands, is that it wouldn't easily fit into the landscape. It takes places where the buffer is a little bit lower than the field, but there are some of these places. And what's certainly true is there's no practice that's going to work everywhere, and so it's really important that we have a lot of tools in the toolkit, and saturated buffers will likely be one of them. I shouldn't say certainly, since the research is still out there.
Thank you, Jane. Okay, any final questions from our audience? Hearing or seeing none. Any final thoughts from our presenters before I go into the upcoming sessions? No. Oh.
No, thanks everyone for joining us.
Thank you all for your wonderful presentations. And thanks to all of you that participated today. Again, please visit the northcentralwater.org website for archived recordings of this session and other interesting water topics, some related to agriculture, some related to urban and urbanizing areas. And our next upcoming session, as I said at the beginning, is on June 17th, 2 p.m. Central, 3 p.m. Eastern, and the topic will be cover crops. And you can see get a quick scan of the rest of them coming up on your screen. Thank you so much. Have a great rest of the afternoon, and hopefully we'll see you at another webinar. Take care, everyone.
Thank you.